Right then. So okay, right. Good evening, everyone. Is my voice clear?
Yes, sir. Good evening.
Okay, right. Yeah, good evening. Oh, thanks for joining the class today. We're supposed to have our class this coming Thursday, but somehow the test two is scheduled on the Thursday evening, so unfortunately, we have to do the class today to finish the syllabus that we need to cover. I do believe that somewhere we did miscalculate the number of weeks, or they bring the test to earlier. I'm not too sure. Has your solid lecturer already get in touch with you all when the class will be started for the second half of your subject here? No? Yeah. Okay. Yeah, I'm not too sure about that, but anyhow, today we have to finish the syllabus. Then we'll do a revision as just like the test one earlier, and then at least your thermodynamics part will be completed. Okay. Right then. So I believe everyone is here. Okay. So then let's start our class. Okay. And you already seen the message in the group that, well, for the guy that shared the information, thanks for sharing that. So your test two will be on coming Thursday, 15th of May. The time would be 9 p.m. to 10:30 p.m. So it'll be 1.5 hour. The location will be P16 apparently. Okay. And since you are section 5, so you'll be going to the room demo 1 then. Okay. There'll be 2 questions for your test 2. Okay. The first question will be on, oh, it didn't say here. Okay, so the first question will be on the closed system. Okay, chapter 4 basically. But of course, to answer chapter 4, you need to understand chapter 3 because chapter 3 was the fundamental of energy. And the second question will be chapter 5, which is what we'll be covering today. It's an open system. Okay, so one question on one question on a closed system. One question will be on open system. Okay, and just to give you a heads up, one system will be in ideal gas, whereas the other one will be on non-ideal gas, which will be a pure substance. Okay. So 2 questions, 1.5 hours. Okay. So after we finish the chapter 5 today, as usual, today we'll break into 2 halves. The first half we'll finish the chapter 5, and then we'll look at the one past year question to perhaps helps you to understand how the best question might looks like, so you can prepare better. Okay. And before we begin, just also want to make an announcement. I received an instruction from the faculty that all the assignment has to be submitted through e-learning. Okay, so I see that a lot of you has already submitted your assignment 1 some times ago before your test 1. I do need you to resubmit that in the link in the e-learning. Okay, so everything in e-learning already being set up. So please resubmit your assignment 1 to the link on the e-learning. Okay, and for the second assignment, which will be the revision for your test 2, which is literally the past year question that we will be looking through today. So that has been uploaded to your e-learning as well. So please get it from there later on. And then after you do it, please submit that in the e-learning as well. Okay. So everything through e-learning. Don't submit through the share folder that I shared earlier anymore. Okay. Because the faculty needs to to keep a record on all your summation. Okay, so please do that. And the due date for the summation for the assignment 1 and 2, I put it until next Monday. Well, anyhow, for your assignment 2 is for your test 2. So therefore, I think logically you should do it, get done before the Thursday anyway. Okay. Right then. So then we move into chapter 5. Okay. Everyone can see the screen, right? Okay. Right then. So chapter 3, we look at energy in general. What are energies? How do we define energy? What types of energy available? All the fundamentals about energy. Okay. And then chapter 4, we look at closed system, basically. Okay. So for closed system, put it simple, there is no mass exchange. Okay. There can be work exchange, there can be heat exchange, but there is no mass exchange, which means the volume is constant. There's no mass go in, there's no mass go out. The volume is always constant. Okay, there can be work transfer to the system or out from a system. Heat can transfer in and can transfer out, but then there's no mass exchange. Okay? And in contrast to that, of course, for the closed system, we look at a pure substance. As a working fluid, we also look at ideal gas. So either closed system or open system, the working fluid can be any substance. If it's pure substance, if it's not ideal gas, then we have to refer to the thermodynamics table to find the property. Okay, but if it's a ideal gas, the gas which is light enough, then we can approximate it with an ideal gas equation. So it makes the calculation for the property slightly easier because there can be we can apply ideal gas equation to calculate the property. Okay. So today we'll be looking at open system. So it's a system that other than there is a energy, other than there's a heat exchange, today this system will have the mass exchange as well. Okay. So that's what the open system is. So when it comes to open system, the first thing that you should remember is the conservation of mass. Okay, we talk about this in the law of thermodynamics before this already. Mass is conserved, energy is also conserved. Okay, so when it comes, because there's mass exchange, so the number one rules that you must remember is mass is always conserved as well. Okay, we'll look at it in detail. What exactly does it mean by conservation of mass? Okay, and then also we have to be always mindful that our analysis, and as far as the syllabus concerned, we are looking at steady system. Okay, steady system means the change of parameter over time is 0, which means there's no parameter change over time. Everything becomes stable. It's steady, which means it doesn't change over time at all. Okay, and this is very important because if it's still changing over time, then we're talking about transient system. The analysis will be completely different. Okay? So we only look at steady system, which means time is not a function for us. We don't look at the system that change over time. Okay. And also, we will be applying the first law of thermodynamics, which is the conservation of energy. Okay. As the statement of the conservation of it's the conservation of energy. We'll apply that to the control volume. So we always have a control volume that we are analyzing. We're not analyzing everything. We always draw a boundary, system boundary. So within the control volume, we'll apply the first law of thermodynamics. The first law of thermodynamics, conservation of energy, and also conservation of mass, basically. Then we'll be able to solve the problem. The conservation of mass is not a constant in the closed system because there's no mass exchange. Everything is enclosed in the control volume. So there's basically no mass exchange. So we don't have to worry about conservation of mass. But now we're talking about open system. There's a mass in, there's a mass out. The conservation must be there. Otherwise, we are looking at a non-solvable problem. Okay. And then we'll be identify the energy, of course, because this chapter 3, 4, 5 is all about energy. Okay. So we're looking at the energy carried by the fluid stream across the control surface, the surface. So when the mass go in, how do we define the energy carries by the fluid? When the fluid go out, how do we define the energy brings out by the fluid itself? And if you still remember the full equation that we were using in chapter 4, we basically write it in a way that Q in minus Q out plus work in minus work out plus E mass in minus E mass out. So this whole thing equal to the change in the internal energy plus kinetic energy plus potential energy. Okay. If our system is not moving, right, the whole control volume is not like moving, there's no change in velocity, then kinetic energy is 0. If there's no change in elevation, the potential energy is also equal to 0. Okay. And in a closed system, mass, the energy due to the mass exchange is also 0 because in closed system, there's no mass exchange. Okay. But in today open system, this will not be 0. So we need to know how to define the energy of mass. Sorry, the energy carried by the mass of the fluid itself. Okay, so that's what it means by the energy carried by the fluid. And that basically will be the sum of the internal energy of the fluid itself, the flow work, the kinetic energy of the flow, not the system. Okay, so these are for the system. The fluid itself, because it's moving, even though the whole system is stationary. Okay, let's say you imagine there's a box, there's a flow coming in, there's a flow going out. The box itself is not moving, so therefore it doesn't possess any kinetic energy. The box itself is not being elevated, so therefore there's no potential energy associated with the box. But then the flow is moving. Okay, so the E, the energy for the mass itself, because the flow is moving, so the flow itself has a kinetic energy. The flow itself might have potential energy. Okay, so the total energy carried by the fluid itself is a sum of all of them, basically. Okay, the same concept generally. Okay, but now we're talking about the fluid, the mass itself only. Okay. And then relate the combination of internal energy and the workflow. Sorry, the flow work, which is the work done by the flow. Okay, to the property of enthalpy. So we'll be looking at enthalpy today. Okay. And then we'll be solving the mass and energy balance problem for common steady flow device. So we'll be looking at a few steady flow devices. Okay. Specifically, we're looking at 4 only: nozzle, diffuser, compressor, and turbine. There are more, but then as I'm being told that it's not in the syllabus of your subject here, because again, you are learning the very fundamental thermodynamics. So there's no point really to go into something too detailed. At least the main steady flow devices has been covered, it gives you an idea how we analyze a open system. I think that will be sufficient. Okay, so that's what we'll be going through in the first half of today class here. Okay, so first of all, let's look at the conservation of mass. Okay, so conservation of mass is quite simple to understand. Let's look at this example here. So when you have 2 kg of hydrogen plus 16 kg of oxygen, okay, so in the end of the day, the combination of them, when they two mix together, I think everyone knows, you get to H2O. So eventually you get 18 kilograms. So the mass is always conserved. You can't destroy the mass as well. If it's in your control volume, it's there. You take it out, then it must become lesser. If you add more in, it become more. Okay, so the mass is always balanced. In a way, it's almost like the chemical equation, the equilibrium equation that you are writing for in your chemical class. So the mass is always conserved. Okay, and mass and energy, some of you probably know, is interchangeable according to this equation here. Okay, we wouldn't go into too detail like into it, but because they behave similarly, they can convert into one another. So therefore, when energy is conserved, mass must be conserved as well. It's as simple as that. Otherwise, where the mass would have gone, right? And in the closed system, as we say earlier, or we call it the control mass system, basically. Okay, so the mass in the system remain constant throughout the process. Okay, but for open system, because only the volume is controlled, only the volume is constant. Mass is not, because mass can come in and out. So we must always keep track the amount of mass enter and leaving the volume. Okay. And how do we define when it's moving, mass is moving? For sure, we're talking about rates, because then it's the mass flow rate. Mass is not stationary anymore. Okay, so the way we define the mass is basically, the mass flow rate is basically through this equation. Okay, it's the integration of the density and velocity over the area. Okay, because in the flow, especially let's say in a pipe, okay, I'll draw it as a pipe like this. Okay, so the velocity, if you look at different location in the pipe, okay, it will not be a constant velocity. Okay, there's always a velocity profile that looks like this. The velocity at the center of the cylinder of the pipe is always the highest, because at where it touched the wall, there is always a friction. So the velocity here is always 0. Okay, and then here is a V max. So this kind of profile is called the velocity profile. Okay, so which means the mass flow rate is also not constant. It should be the highest at the center, because that's where the velocity is highest. So the actual mass flow rate should be the integration. Integration means if you cut this area into a smaller section, each of it you can know the velocity at that point, and then you can sum them all together in a way. That's what integration means. Okay, but unless we analyze the whole system in 3 dimensions using finite element method, otherwise most of the time, more conveniently, we're expressing the mass flow rate in this equation only. Okay, so we're taking a average velocity. So mass flow rate is as simple as density multiplied with the average velocity multiplied with the flow area. Okay, and A is a flow area. It's basically this area. Okay, the circular cross section of the pipe. that's where the flow is perpendicular to. Okay, and it's quite important to call this the flow area. It's labeled as AC here. Okay, it's sometimes they call it also the cross section area. Okay, so this is basically the flow area. Because there is another area that apply here, which is the area, the circumference. Okay, this flow area is basically pi d square over 4, okay, if this is diameter. Okay, there is another area, which is a surface, which is a pi d, the circumference, multiply with the length. Okay, so this area, we call it the wetted area. It's an area wetted by the flow. Okay, not too much of your concern here, but this cross-section area is important when we analyze the heat transfer, because this is the area that come in contact with the surface, with the flow. Okay, so here we're only dealing with the flow area. Okay, but just to differentiate it, to let you know that there is actually another area called the wetted area. Okay, but for the flow rate, we'll be looking at the cross-section area that's perpendicular to the flow. Okay, and density is basically mass over volume. Okay, or in other words, it's also 1 over specific volume, because specific volume is basically the total volume over the mass. Okay, so this is another relationship that you probably will want to remember. Density is basically equal to 1 over specific volume. Okay, so this is volume flow rate. If we want to define the volume flow rate, then is really using this equation, because the definition of density can also be expressed in the rate. It's no problem. Okay, so then volume flow rate is basically m dot over the density. Okay, so then we'll get to velocity multiplied with flow area only. Okay, so volume flow rate is basically how fast this volume of air is moving inside the pipe. Okay, so it's either in meter cube per second or in kilogram per second only. So that's the how we calculate the mass flow rate and the volume flow rate. Okay, and when it comes to the conservation of mass, okay, you can imagine a bathtub like this. Okay, where one side you have the water flowing in, and then let's say you don't close the drain. Okay, of course, if you close the drain, you can notice the water sure will increase the water level. Okay, because the conservation of mass basically tell us that this the mass in minus mass out equal to the change in the mass in the control volume. Okay, so in this case, the control volume is the bathtub itself. So that's our control volume. If you close the drain, which means there is no mass out and there is a mass in, so sure enough, this will increase, the water level will increase. But if you open the drain, which means this will not be 0, okay? If they are equal, which means you add the water as fast as the water flow out, then the water level will stay constant. Okay, but if you close the water now, you only open the drain, then this water level will sure decrease. Okay, so that's what conservation of mass basically means. Okay, so it's the change in the mass in the control volume is always the difference between the mass come in and the mass that goes out. Okay, and you can express it in the mass only, in kg only, or of course you can express it in the rate as well. The mass flow rate in minus mass flow rate out, it must equal to the rate of change of the mass in the control volume. Okay, so this equation is basically the conservation of mass equation, or the mass balance equation, sometimes we call it. Okay, it's a quite straightforward concept actually. It's not nothing too complicated. So it's just, in fact, thermodynamics are quite straightforward. It's just that you need to know which type of system, which principle apply. I think that is probably the more confusing part, which may need some times for you to get used to it. Okay. Then we talk about steady flow process or steady flow system. Okay. So steady flow basically means the parameter over dt equal to 0. Okay, and the parameter can be any parameter. In this case, it can be the mass. So which means for steady flow system, dm control volume over dt must be equal to 0. That's how we define steady flow system. dp over dt must be 0, no pressure change. dt over dt must be 0 as well. Okay, in fact, dE over dt must be 0 as well. Okay, so there's no change in the pressure, temperature, energy in the control volume, everything in the control volume. Okay, no change in the mass. Only then, over time, of course, then we can call it a steady flow system. The example just now, if you close the drain, you don't let the flow go out, there is the delta M in the control volume over time. So therefore, that is not a steady system. If you close the water tap, you open the drain, there is also a dm in the control volume over time. So therefore, it's not a steady system as well. Okay. If you have mass in equal to the mass out, they balance it out, then dm over dt equal to 0, then it is a steady system. Okay, so steady system basically means there's no change in the parameter. Sorry, no change of parameter over time. That's how we define steady system, steady flow system. Okay, so which means in steady flow system, for instance, like this, if here go in 2 kilogram per second, here 3 kilogram per second, then the one go out must be the sum of them, which is 5. Only then the dmcv over dt can be equal to 0. Okay, so in this kind of system, if it's a single stream, which means one in, one out, m1 equal to m2. Sorry, m.1, the mass flow rate coming into here, equal to here. Okay, if we write 1 for this, then m1 plus m2 equal to m3. Okay, this is a conservation of mass for this system. Okay, and individually, m.1 equal to rho VA at inlet number 1 here. Sorry, this system here, I have to draw it to be like this. Okay, so this is m.1, this is m.2. Okay, So the mass flow here is really the row 1, A1, B1. Here will be row 2, A2, B2. So if it's a steady flow system, then this must equal to this, because then the dm over dt in the control volume is 0. Okay. Multiple inlet exit, then it's a sum of all the inlet equal to the sum of all the outlet. Okay. If there's another fourth one here going out, then you must plus the M4. Okay. The only exception, in fact, not exception, just a special case, okay? This equation here basically means that density can change. When density can change, that basically means it's compressible or expandable, okay? The density basically means how much the mass in the same amount of volume. If you compress it, which means density will increase. If you expand it, which means density lower, okay? So when it comes to incompressible flow, which we know most of the liquid are incompressible, which means density doesn't change so much. So when density doesn't change so much, this equation got reduced to this. Okay, because now rho 1 equal to rho 2. Okay, so in the incompressible flow system, the volume flow rate is also equal to one another. Okay, but we don't call it the conservation of volume. This doesn't exist. Okay, it's just a conservation of mass under a incompressible flow condition, which makes the volume flow rate equal. Okay, between state 1 and state 2. Okay, but it will not be the case for compressible flow, because for compressible flow, density can change. Okay, so it's just a very special case only. So far, so good about the conservation of mass. Any question up until this point? Anything not clear? Okay. Right, nice. Right, I spent quite a bit of time to talk about the conservation of mass because that is the additional principle applied on top of what you learn in chapter 4 in order for us to look at the chapter 5 here, which is control open system. Okay, so let's look at one example here then. Okay, so here it says that a garden hose is attached to a nozzle. Okay, garden hose attached to a nozzle. Okay, I think everyone played this before. Okay, and we use that to fill a 10-gallon bucket. Okay, the inner diameter of the hose is 2 centimeter, and it reduced to 0.8 centimeter at the nozzle exit. Okay, if it takes 50 seconds to fill the bucket with water, determine two things. One is the volume and the mass flow rate of the water through the hoses, through the hose itself, not the nozzle. Okay, and second, the average velocity of water at the nozzle exit. Okay, so to put it simple, it is a, you can imagine like this. This is a nozzle. Okay, so this here diameter is 2 cm. Okay, and here the outlet D2 is 0.8 cm. 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 0.8 Okay. And for us to find out the mass flow rate here, okay, so we don't know the mass flow rate, but then we know the volume flow rate of to fill up the water. So the volume flow rate, as you can see here, is basically the volume over the time. So 10 gallon of bucket, 10 gallon, if we convert that to liter, which is something that is more conventional for us to use SI unit. Okay. So 1 gallon is 3.78. Okay. This sometimes the conversion rate, just have to remember that. Okay. If not, then the question should give you, or the question shouldn't be in gallon, in fact, at all. This textbook is from US because they are using gallon here. Okay. But then from here, you know the volume that you're filling up in the time, which is 50 seconds. So from there, you can basically get the volume flow rate, which is 0.757 liter per second. Okay. And mass flow rate is basically density multiplied with the volume flow rate. Okay. Or the other way around, we write it usually is this. Okay. So we know this volume flow rate already. If we know the density, then we can know the mass flow rate. Okay. So density for water is quite standard. Is incompressible, almost incompressible, which is 1 kg per liter, or 1,000 kg per meter cube. Okay. 1 meter cube is 1,000 liter, basically. So therefore, you get 1 kilogram per liter. That's the density of liquid, of water, sorry. Okay. So then you multiply density with volume flow rate, you get to the mass flow rate, which is, this one is wrong, should be kg per second. So you get 0.757 kilogram per second. Okay, so that's the mass flow rate and the volume flow rate, which is what the question wants us to find out. Okay, through the hose. What about the velocity? If you want to find out the velocity inside the hose, okay, so that would be rho A V1. Okay, so density of water, which is 1,000 kg per meter cube. Area in the at the hose, diameter is 2 centimeter, so therefore pi 0.02 pi d square over 4. That will be the area of the hose, multiply with V1. M1 we already know. So then we'll be able to find out the velocity at the hose. Okay, but that's not what the question wants. The question wants us to find out is the velocity at the nozzle. And because this is a steady system across the nozzle, the bucket is not a steady system because the water level is changing, right? There's mass in. There is no mass out. So the bucket itself, if our control volume is the bucket, then it's not a constant. It's not a steady system. Okay. But for the hose, yes. Mass in equal to mass out. We look at across the nozzle, which is what I'm drawing here. Okay. So this is the dm control volume over dt is 0. The water from the hose come in, it goes out from the nozzle right away. Okay, so which means M1 equal to M2, M dot, same thing. Okay, now we're talking about the rate. So then M2 is equal to rho 2 A2 V2. Okay, density remain the same. Area, now pi, the diameter for the nozzle is 0.8 centimeter. So therefore 0.008 square over 4 V2. Okay, so then you'll be able to find out how much is V2, which should be this. Okay. So really when you analyze a system, is quite important for you to look at where is your control volume, where is the boundary that you are analyzing. Okay, so here the focus is actually the nozzle. Okay, if we are looking at the bucket itself, okay, there is a M1 mass in. Okay, mass out equal to 0. Okay, so then mass in minus mass out equal to dm cv over dt. Okay, so this is 0. So M1, which is this value, equal to the change of the mass in the tank. That's what we apply here, basically. Okay. So for the tank itself, it's not a steady system. There is a change in the mass. Okay, but across the nozzle, there's none. Okay, so that's what this example is trying to show you. Okay, so far, can you understand about this example? Okay, good. Right then, so let's look at the work from the flow then. Okay, so now we know how to find the flow rate, how to apply the conservation of mass. So next, let's look at how we evaluate the energy, the work done by the flow. Okay, so it's just flow moving. Okay, so how come there's any work? There's a question asking, is the 1 gallon equal to 3.78541 liter a fixed number? Yes. That is a imperial unit to SI unit, yes. The conversion is a fix. It's like 1 inch to centimeter. Okay. But don't worry, all your question in the test, in your assignment, everything will be in SI unit. You don't have to remember imperial unit conversion. And it shouldn't appear as well. Our syllabus is all SI unit. Okay, it just happened that this textbook use imperial unit. Okay, right then. So yeah, how just a flow moving. How is there any work involved? Okay, so you can imagine it like this. Okay, so you have a control volume already in your system. Okay, so when the flow goes in, it's almost like there is a imaginary piston pressing another volume of air into your existing control volume. And that's where the work actually happen, because it's actually literally like pushing new amount of air, new amount of fluid into your existing control volume. Okay, so then the work itself is basically equal to the F. Sorry, the force to force it, to push it in, is basically the pressure multiplied with area. Okay, and then the work itself is the force multiplied with the length, because F work is force multiplied with distance. Okay, so therefore it's P A pressure multiplied with the area, which is this area, the cylinder area. Okay, multiply with the length, how much the length is, it actually push it through. Okay, and this area multiplied with this length is basically the volume. So the work, the flow work, okay, this is called the flow work. Okay, we literally write as W flow is basically equal to the pressure multiplied with the volume. Okay, when you push the air in, which is equal to the mass in, okay, sorry, there's no rate here, so I should just write is in mass in. Okay, so mass in is pushing air in into the control volume. Okay, equally, if mass out, it's like the volume is pushing, the control volume is pushing the air out from it as well. So then we define the same way as well, pressure multiplied with the volume. Okay, just that now it's negative. When it goes out from the control volume, it's negative. Goes in is positive, basically. Okay, that's how we write the equation as well. It's always the, sorry, let me just go back to here. Okay, so you see it's always in minus out, in minus out. Same goes for here, in minus out as well. Okay. Okay, so that's basically what a flow work is, or flow energy, sometimes we call it. Okay, but this energy is really in terms of work, because it doesn't involve in the change in temperature. It's not heat for sure, so therefore it's a work. Okay, but that is not the total energy of a flowing fluid. Okay, the total energy in the flowing fluid is, we call it the E. Okay, total energy is equal to the internal energy of the fluid itself plus kinetic energy. U is internal energy plus kinetic energy of the fluid plus potential energy of the fluid. Okay, the fluid is moving. Okay, not the system kinetic energy. The system is stationary. The control volume is stationary. It's not moving. Okay, and it's not changing elevation as well. Okay, now we're talking about just the fluid itself. So the fluid is moving, for sure it possesses kinetic energy. Okay, depend on the situation, but most of the time there is no potential energy in the fluid. Okay, because it doesn't involve change in elevation unless there is. Okay, I think one of the example later on, you can see there's change in elevation in the fluid itself. So then there's a potential energy change. Okay, but the total energy in the fluid itself is the internal energy plus kinetic energy plus potential energy. Almost the same when we define the system as well. Okay, and if we write everything in specific form, which means over mass, okay, then it's U plus kinetic energy, specific kinetic energy, V squared over 2, and specific potential energy, gravity time altitude, Z, elevation, sorry. Okay. And then we can simplify it according to this here. Okay, because we want to make H, we want to introduce a new parameter, H equal to U plus PV. Okay. If we just leave it as it is, okay, the total energy of the flow itself, we write as theta, is basically equal to the flow work itself plus the E, okay, which then we can expand into like this. The PV from earlier, because it's moving, is pushing into the boundary, okay? So then we rearrange a bit. H is basically the enthalpy equal to U plus PV, which is this part here. So then the final equation for the total energy is basically enthalpy plus kinetic energy plus potential energy. Okay. Or we write it as this, H plus V squared over 2 plus GZ. GZ is a potential energy, basically. Okay. And we can also write it in the absolute terms, which mean M multiplied with usually M dot, yeah, equal to M dot multiplied with H plus M dot V squared over 2 plus M dot GZ. Okay, then everything we write in capital. So now this is H plus kinetic energy plus potential energy. Okay. Generally, we can write it without the mass, or we can write it with the mass. Okay, it's either the specific terms or the absolute terms something. Okay, right. So this is the total energy associated with the flowing fluid itself, which is the E mass that you see earlier. Okay, which E? We just go back to here. This E and this E. Okay, of course, here is the absolute term. What we see just now is the E mass in. This is E mass out. Okay, over mass, it becomes the small capital. Okay. So then if we look at non-flowing system, which is closed system, and flowing system, okay. So for flowing system, of course, this theta equal to PV plus U plus KE plus potential energy. So then we make it into this. Okay. Whereas for non-flowing system, which is closed system, PV plus U plus KE plus PE. Okay, so PV is 0 because for non-moving flow, there is no workflow at all. Sorry, the flow work, not workflow. Okay, there's no flow work at all. So then it becomes U plus kinetic energy plus potential energy. Okay, so for non-flowing fluid, we definitely write as E, but then just to differentiate it, here we write as theta. Okay, but it's literally the E basically. Okay, so it's really the same E that we're talking about here. which is what you can see here. The E mass is really m multiplied with theta. Okay, if we multiply with m dot, which is the flow rate, mass is just kg. If we're talking about kg per second, which means time come into picture, then we get the E dot mass. Okay, E is energy, so therefore unit kilojoule. E dot is the rate of energy change, so therefore kilojoule per second, hence kilowatt. Okay. When the kinetic energy and potential energy of the fluid stream are negligible, of course we cross that out, then we get to this only. Okay. So it's really just equation. If it comes 0, then of course we reduce to this. Okay. Sometimes we do calculate it this way because the magnitude of them one of them can be much more significant than the other, which means the kinetic energy, the velocity will be very small. So the kinetic energy is very, very small. Potential energy, maybe there's none at all. So therefore, reduce it to just the mass multiplied with the enthalpy. Okay. And this is applicable to both ideal and non-ideal gas, which means for all the pure substance that we're talking about. Okay. If it's because it's applied to pure substance, so therefore to get the H, we have to refer to the property table. Okay. For us to get the H. Unless if it's ideal gas, then we can. If ideal gas, then we can use ideal gas equation. Okay. Special case. Otherwise, all the time we have to refer to property table for us to get the property, the enthalpy, basically. Okay, so let's look at one example then. All right, another example that concerning this. Okay, so here it says that a flow steadily, the air flows steadily, okay, in a pipe at this pressure, this temperature, this velocity. Okay, so in a pipe like this, 300 kilopascal, 77 degrees Celsius, and 25 meter per second. Okay. Maybe I should just write it properly. P1, 300 kilopascal. P1, 77 degrees Celsius. V1, 25 meter per second. Okay. And the flow rate, M1, is 18 kilogram per minute. Okay. The question wants us to find out the diameter of the pipe. Okay. Then the rate of flow energy, which means the work, the flow work. Okay. This is the flow work. Okay. And then the rate of the energy transport by mass, which means the total E. Okay. Transport by the mass. Sorry, rate of energy. So therefore E dot. Okay, the total energy in the flowing fluid. Okay. And then last, the error involved in part C, which is this one, if kinetic energy is being ignored. being neglected. Okay, because we know this should be E equal to this full equation. Sorry, this E dot. Okay, so it should be M dot H plus B squared over 2 plus GZ. Okay, but part B wants us to ignore this. Then see what will happen. Okay, so one by one, let's start by finding the area. Okay. So the solution is here as well. Okay, but I myself probably will do it slightly different. Okay, so for me, M1 equal to 18 kilogram per minute over 60 kilogram per second. Okay, I always like to change to SI unit first, so I don't get confused. Okay, so this equal to rho 1 A1 D1. Okay, and this is A. Okay, so therefore A is, because A is ideal gas, so therefore the density I can calculate based on, sorry, I'll just write here because it's density for stage 1, P over RT. Okay, because for ideal gas, P1, B1 equal to M1 PV equal to MRT. Okay, so then mass over volume is P over RT, basically. It's ideal gas. It's A. Okay, that's very important. You have to know what is your working rate, and then what kind of assumption you can apply to it. Okay. So then density I can find, no problem. Velocity, I have the number. So then I'll be able to find out how much is my area. So that will be pi d squared over 4. So from there, I can find out my area, diameter. Okay, so then I can find out this, which if you try it, you should get this number. Okay, so later, the exact calculation, I'll leave you to try it later on. Okay, right then, so that's how we can find out the diameter of the fluid here. Okay. Second is the flow energy. Okay, so for flow, we know that is basically m dot multiplied with PV. Okay, because is this equation. Okay, so then you can see here the solution, m multiplied with P, which density you already calculated just now. Okay, so from there you'll be able to find out the rate of the flow energy. Okay, so that's how we find out the flow energy. And last is the total energy transport by the mass. So then we write the full equation here. Okay, of course there's a plus PE as well, but then potential energy, since there's no change in the elevation in the flow, so therefore it's basically 0. Okay, and then here the enthalpy instead of looking from thermodynamic table because it's ideal gas. So then H equal to Cp multiplied with T. It can be approximate to Cp multiplied with T. Cp is the constant specific heat, constant pressure specific heat. T is the temperature. So then if you calculate everything, you should get this number. So that is the total energy transport by the mass. Okay. Flow energy plus internal energy plus potential energy plus kinetic energy. Okay. Internal energy plus the flow energy, of course, equal to the enthalpy. So that's how we evaluate it. Okay. And D, the question wants us to ignore the kinetic energy. If we recalculate again without the kinetic energy, you find out this number, which is not very far off from this. Okay, the error is only 0.09%. Okay, because the magnitude of the enthalpy is much larger than the kinetic energy. So depend on the situation. Sometimes the enthalpy is much larger, so then makes the kinetic energy insignificant. Okay, but the best is to calculate them, even though the magnitude is small. If it's there, usually we just calculate it. Okay, in this case, like it's very clear, there is no elevation change. So therefore, PE is 0. Okay, but kinetic energy definitely is there is a kinetic energy here. Okay, so even though it's small, sometimes most of the time we will just calculate it. Okay. Right then let's look at another example. Yes, one more example before we move into the energy analysis for steady flow system. Okay, so quickly here. Now this is a steam. So a steam is a pure substance. It's not ideal gas. So therefore, any property we have to look from the steam table, the thermodynamic table. Okay. So here it says that steam is living at a 4-liter pressure cooker. Okay. Operating pressure 150 kilopascal. Which means inside here is 150 kilopascal. Okay. It is observed that the amount of liquid in the cooker has decreased by 0.6 liter in 40 minutes. So then that gives us the volume flow rate basically. Okay. After the steady operating conditions are established. So this is under steady state condition. Okay. So then the volume flow rate is 0.6 liter over 40 minutes. That's the volume flow rate. Okay. And the cross-section area of the opening is 8 millimeter square. Okay, so cross-section area is available. So what is the mass flow rate of the steam and the exit velocity? That's what the question wants us to find out first. Okay. Second, the total and the flow energy of the steam per unit mass. Which means the question wants us to find out the E and the flow energy, which is the W flow. Okay, total energy I'll just write as E. Or earlier they write as theta. Okay. And then number third, the rate of which energy leave the steam cooker. So which means this will be the total E dot temp. So three things we have to look for it. And because this is steam, so therefore we have to look at the property table. Okay. So if we look at the property table, okay, you can see here the property. Okay. So at 150 kilopascal, okay, Vf this value, Vg this value, Ug this value, Hg this value. G is the gas, F is the fluid, saturated, saturated liquid, saturated vapor, saturated vapor, saturated vapor. Okay. So we know the volume flow rate, but then we have to change it to mass, basically. Okay. So then, which means we have to multiply with density, or 1 over V. Okay. And because this is steam that exits the cooker here, so therefore this is for the fluid itself. Okay. So then from there we get this number 0.5, and over 40 minutes, then therefore we'll get this. Okay. So that's how we get the mass flow rate, basically. So it's really just changing the unit only. Okay. And then how about the velocity? So the velocity is basically rho a v. Okay. And rho excuse me. Okay. Okay. Sorry, here we are using the density for the fluid because the question say that the amount of liquid in the cooker is decreasing by this much. So this volume represent the volume of the fluid itself, the liquid itself. Okay. So the mass go out equal to the mass here. Okay. So this is equal to M1, also equal to M2, or more specifically, equal to Mg, equal to Mf. Here is the gas, here is the fluid. Okay. So same number here, we can apply to for the gas. Okay. Because the opening is 8 millimeter. So this area here, we have 8 millimeter square, which what goes through it is actually the steam. So it's the gas. Okay, so from there, we'll be able to find out what is the velocity. Because the rho for G, this can take it as 1 over V G as well. Okay. So then we'll be able to find out how much is the velocity of the flow. of the steam that run through the opening. That's 0.0, the 8 millimeter square of area. Right? So that's how we find out the flow rate and the exit velocity. So then is the total and the flow energy. Okay. So maybe let's find the flow energy first. Okay. So the flow energy, oops, it's not written here. Okay. So the flow energy, okay, is actually equal to PV. Okay. And we also know that H equal to work, the flow energy plus internal energy U. Okay. So therefore, for us to get this, is basically H minus U. Okay. And we're talking about the one that goes out is the gas. So therefore, we are using the property of the gas to calculate this. Okay. Which, if we look out from the thermodynamic table, we have the Hg and Ug, the saturated vapor, basically. That will give us this. Okay. And then the total energy, theta, is defined by this. H plus kinetic energy plus potential energy. Kinetic energy is close to zero, as we know. Okay. So we can approximate it equal to H. This is definitely zero. Or we can include that as well. It's not a problem. We already have this. So this can be the V G over 2. Okay, so then you get a additional 0.588 to this. Okay. So again, for me, I will just include that in, since we know that it's always enthalpy plus kinetic energy plus potential energy. And then the rate of which the energy leaving the steam cooker, the cooker by steam, okay, is basically this theta multiplied with the flow rate, the flow rate that we calculated earlier. Okay, then we get the actual kilowatt of energy, the rate of change of energy leaving this pressure cooker through the steam, basically. Okay, right? So that's how we can solve the question, really. So time is about finding the state, basically. How do we find the state? Then we'll be able to calculate the parameter. Okay. Right then. Any question up until this point? Is everyone still following me? Understandable, right? I do realize it's a bit boring. It's a thermodynamics after all. Okay. Well, I hope you can understand well. I think that's the most important. Okay. And then going back later on, you can give it a try again on this example by yourself. Okay. Okay. Right then. How to know V represent velocity and volume? That's a very good question. Um, mm, mm. I would say, I would say, yep, I think throughout the knot here, if its velocity is this writing of V, okay? Whereas for volume is this, yes, is this a curvy volume, V. So this is volume, this is velocity. Yes, it's a bit difficult to differentiate. Yes, I agree. And there is no specific velocity. There's nothing so-called specific velocity. So therefore, yes, you don't have a small cap velocity. So all these curvy V are standing for volume, specific volume. The small cap curvy V, specific volume. The large curvy V is the total volume without the sheriff. It's the sans serif font. Is that okay? Okay. Well, a lot of time in thermodynamics especially, we're running out of a symbol to represent. Okay. In this, sometime we do use U to represent velocity as well, but in this case, we can't because there's internal energy using U already. Okay. So yeah, the volume is the curvy sans serif V, whereas the velocity is a serif V, the straight V. Okay. Right then. So I think let's look at how we analyze steady flow system then. Steady flow open system. Okay. So we look at how we define energy already. The work, the flow energy. Okay, the flow work basically, and then the total energy in the flowing fluid. So we look at conservation of mass, we look at how we define the energy of it. So then let's apply that to a steady flow system then. Okay. So steady flow system, basically volume is constant, mass is constant, energy is also constant. Okay. So the conservation of energy, conservation of mass has to be applied. Okay. And the fact that volume is constant means that boundary work is also zero. Okay, boundary work is the expansion of boundary. That the work done by the boundary itself. Since now the boundary doesn't expand, volume is constant, so therefore boundary work will be zero, unlike the closed system that we learned before. Okay, so here there's no boundary work, but then we have a flow work. Okay, so steady again is no change in time basically. Okay, so then the equation that we are applying here, okay, pretty simple. It is still okay. I'll just write the E mass as E, so is shorter a bit. Okay. Okay. Right, and then because this is the system potential energy, system kinetic energy, as long as this system is not moving or there's no elevation change, velocity 0, elevation change 0, so then we have this to be 0. Okay, and because it's a steady flow system, so the change in the energy is also constant, so therefore this is constant as well. Okay, which is why here we also write as 0. Okay, so really what we end up with is everything here equal to 0. So this has to be balanced across, as simple as that. Okay, which is why if we rearrange it, what we'll get is Q in plus work in plus energy due to the flow carried by the flow in has to be equal to the energy out, work out, plus the flow energy carried by the flow going out from the system. Okay, so it's really in equal to out. Conservation of mass, conservation of energy combined together. Okay, so that's the equation that we'll be using to analyze a steady flow process or steady flow system. Steady flow open system. This is the equation that we'll be using. Okay, and m dot theta. Okay, so m dot multiply with enthalpy plus kinetic energy of the fluid, not the system, the fluid itself. Okay, plus the potential energy of the fluid. Okay, same goes for this side. So this is the one that we were looking at just now, how to define the energy in the flow. So now we apply it here. Okay, so the whole system basically is still based on the equation that you seen in chapter 4, basically. Okay. And sign convention, well, I think the easiest is if the work go in, energy go in, then it's positive. If they go out, it's negative. I think that's much easier to remember. Okay. And of course, everything can be expressed in specific term as well. It's not a problem. Okay. If we divide over mass flow, depending if we are talking about the rate of energy transfer, we divide it by mass flow rate, then we get the specific heat. If you're talking about the power, rate of energy transfer, rate of work transfer, divide by the mass flow rate, then we'll get the specific work, basically. Okay. So this equation really can be in the absolute terms or in the specific term. Okay. So let's look at a few steady flow devices then. Okay. In fact, is actually quite a few example, so it's quite long. And I notice it's already 9:30, so I trust that it's also quite tiring by now. So why don't we take like a 10 minutes break? So now it's 9:37. Let's say 9:40. Okay, so let's come back by 9:50. Go refresh yourself. Then we'll go into the steady flow devices. Is that okay?
Yes, okay.
Okay, right. So I'll see you in 10 minutes time. which is what you can see here. The E mass is really M. Okay, right. Welcome back. So let's continue then. Okay, right. So next, let's look at how we can apply what we learned just now to some of the steady flow engineering device, open system specifically, okay, where there's a mass exchange. Okay, and we'll be looking at a few examples: nozzle, diffuser, turbine, and compressor. Okay, but there are more examples such as heat exchanger and pump, but we won't go into every single one of them, mainly because of the time constraint as well. So we'll look at the general concept, and then you should be able to apply to the rest of them. Okay, so just remember, all these devices, all these systems, we analyze it under steady flow. So which means the change of mass in the control volume over time is always zero. Okay, so in a way, there's no mass accumulation in this kind of system when we analyze them. Okay, so first of all, nozzle and diffuser. Okay, nozzle, we've seen the example before. Okay, so it changed the velocity. Across this device, this control volume, okay, the property will change. Specifically, nozzle increase the velocity. So when velocity increase, pressure will drops. Okay, so sometime when engineer need to speed up the flow, we'll use a nozzle. We change the area. Of course, area will be different as well. This is A1. This is A2. So area will be different as well. So by changing the area, we can manipulate the velocity, we can manipulate the pressure. Diffuser is the opposite. We slow down the velocity so that the pressure can build up. Okay, cause the area will be different as well. So it's really just two opposite devices. Nozzle to increase the velocity, diffuser to increase the pressure. Okay. And one thing for sure about nozzle and diffuser, work is zero because there's no work transfer in the process. Nozzle and diffuser doesn't do work at all. Okay. But there might be heat exchange in the process. There might be, depending on whether it's an adiabatic nozzle, adiabatic diffuser or not. Okay. If it is fully insulated, if the question says it's fully insulated or it's adiabatic, then this can be zero. Okay. It depends on whether it's insulated or not. Okay. When there is no heat transfer, then the equation really reduced to this only. It's only the energy exchange throughout nozzle and diffuser is really just because of the mass itself. If it's an adiabatic nozzle and diffuser. Okay. One thing for sure, doesn't matter it's adiabatic or not, work transfer always equal to zero. Okay, so this one thing that you should know about nozzle and diffuser. It changed the property, but then it doesn't involve in any work at all. Okay, potential energy, most of the time elevation doesn't change. The nozzle is not moving as well, so potential energy, kinetic energy of the system is always zero. Okay, this here, this is for the system. This here, the small cap one, they are referring to the flow. So the change in the flow kinetic energy, there is, but then change in the potential energy in the flow is zero as well. Okay. So quickly, let's look at one example. So this is a diffuser in the aircraft engine. Okay. So diffuser and nozzle is quite commonly used. In fact, not commonly used. It's in fact being used in the aircraft engine, the same aircraft that everyone takes when we go travel. Okay. So it says that air at 10 degrees Celsius and 80 kilopascal enter a diffuser of a jet with a steadily with a velocity of 200 meter per second. Okay, inlet area. So it's a diffuser. So I should just draw like this. Okay, 10 degrees Celsius, 80 kilopascal. Velocity is 200 meter per second. The flow go in. Okay. Inlet area 0.4 meter square. I should write this properly. V1. Straight V. Okay. And then A1. The air leaves the diffuser with a velocity that is very small compared to the inlet velocity. Okay. So going out here, V2 is almost zero. That's what the question say. Okay. So determine the mass flow rate of the air and the temperature of the air leaving the diffuser. Okay. So the mass flow rate is basically we can analyze from the inlet because the inlet has most of the property that we need. It's rho 1, A1, V1. Okay, V1 we know, A1 we know. Rho is basically P1 over RT because this is air. It's an ideal gas. So therefore we can apply ideal gas equation for it. Okay, so that's how we can find out the mass flow rate at the inlet of the diffuser. Okay, and this is our control boundary, by the way. Okay. Then how can we find out the temperature leaving the diffuser? This is a steady flow device, so therefore M2 got to be equal to M1. Okay. And then we have to write the energy equation, which looks like this. Okay. And here, there is no heat transfer involved, not being mentioned. For diffuser, definitely the work transfer is 0 as well. So therefore, we come to this equation here. Okay, so H1, we can calculate based on CP T1. Okay, and H2, obviously, we can calculate based on CP T2, which T2 we don't know it, T1 we know. Velocity 1, we know. Velocity 2, the question say is very small, almost 0. So we can treat it as 0. Okay, so we rearrange it, the whole thing. Here, the mass got cancelled out. Okay, even if you don't get cancelled out, you know the number. So we can just plug it in, but you can be cancelled out anyway. Okay, so then eventually, you will get to the T2, which is about this temperature. Okay, so that's how we can solve a problem for diffuser. If it's nozzle, pretty much the same way as well. Okay, so you can see the pattern is always you find out the state at one side first, and then you relate the second state using the energy balance equation. Most of the time, that's how we solve a open system. Okay, even the closed system, pretty much the same method as well. Okay, that's how we solve thermodynamics problem in general. We find out the one state first, because from state 1 to state 2, in between, this is the process. Okay. Here is an example of nozzle. Okay. So here is a steam. Okay. So steam means that we have to find the property using steam table, thermodynamic table. We cannot apply ideal gas equation here anymore. Okay. So here as well, steam at this temperature. Okay. Sorry, this pressure, this temperature, steadily enter a nozzle whose inlet area is this much. So now this is a nozzle. So I'll draw in a nozzle way. Okay. So P1 is 1.8, sorry, megapascal. T1 is 400 degrees Celsius. Okay. Area 0.02 meter square. Okay. The mass flow rate is 5 kilogram per second. So M1 is 5 kilogram per second. Okay. The steam leave the nozzle at 1.4 megapascal. So P2 is 1.4 megapascal. Velocity 275 meter per second. Okay. So here there's a heat loss from the nozzle per unit mass is this much. So then there is a Q out, which is 2.8 kilojoule per kg. Okay. So the one earlier is adiabatic because Q is 0. It basically means will be insulated. Okay. But here, not for this nozzle. There's a heat loss, basically. Okay. So A, determine the inlet velocity. B, exit temperature of the steam. So more or less like earlier. Okay. So to find out the velocity, here we can using this equation still. Okay. The difference here is density. We cannot use P over RT because this is ideal gas. It's wrong to apply this equation here. This is steam. It's not ideal gas anymore. Okay. So then for density here, we have to use 1 over specific volume. Okay. So first we need to find out the state of the steam first. Okay. So we have this pressure, we have this temperature. So if we look at the thermodynamic table, okay, you will find out that the specific volume and specific enthalpy is this number. Okay. In fact, if you look at this pressure and temperature combination, you'll find out that the steam, I think, should be superheated. Okay, so you're probably looking at the superheated steam. So at this pressure, this temperature, this is a specific volume, this is the enthalpy. Okay, so then this will be F. In fact, I can't write S, sorry, not F. It's not G even. So this will be 1, this number. Okay? It's a superheater. So therefore, you can see this equation here. Then you'll be able to find out the velocity. Okay, I'll go through quite quickly because there are still quite a few examples that we have to go through. So I'll just roughly explain the step. Then later on, you try yourself. Okay, it's good to try as well because this can be how the test question will look like as well. Okay, so then once you find out the state 1, then we write the energy balance. We should be able to find out the second state. So T2. Okay. Then we apply the equation. Okay. So the full equation again is Q in minus Q out plus work in, work transfer out plus E in minus E out. So all this equal to 0, okay? Because change of internal energy, change of system kinetic energy, change in system potential energy, all are 0. Okay? And here, there is a Q out, there's no Q in. There's no work transfer because this is nozzle. Okay? So therefore, it get reduced to this if we express it in specific terms. Okay? So then you plug in the number. You should be able to find out that the enthalpy at the outlet is how much. Okay? Here, H is not equal to CPT as well because this is again ideal gas equation. We cannot apply it here. This is steam. So therefore, once we find out the H2, we have to use property table to find out at this pressure, this enthalpy magnitude, what is the temperature. You might need to interpolate between different temperature to get the correct temperature for T2. Okay, so this have to be based on the steam table. Okay, because again, here, this is steam. Steam is not an ideal gas, so we can't apply ideal gas equation. Okay, just remember that very well. If it's not ideal gas, we cannot apply ideal gas equation. We must refer to the property table. Okay, so that's what nozzle and diffuser is. It changed the flow property, but there is no work transfer in the process. Okay. Then next, turbine and compressor. Okay. So unlike nozzle and diffuser, turbine and compressor is meant for work transfer. Okay. In fact, turbine is, we use it to transfer the work. Okay. Work is done by turbine. So from the flow, we transfer the work. The flow do the work, and then there is a work out for sure for turbine. Okay. For compressor, we give a work in for it to do the work to the flow. Okay. Compressor air, basically. Okay. It brings the flow to higher pressure or higher flow rate. Okay. Turbine, quite the opposite, is driven by the pressure. From the pressure, the flow develop, and therefore it delivers the work transfer. Okay. So they are opposite as well. One, you give the work to do work to the flow, and turbine, the exactly opposite. The flow do the work, transfer the work out from turbine. Okay. And how this is being drawn, in fact, is not correct. I don't agree with this. For turbine, we draw like this. This is 1, this is 2. Okay. And P1, P2, P1 always larger than P2. Okay. Mass has to be conserved. Okay, because it's still a steady system. For compressor, sorry, here there's a work out. Okay, whether or not there's a Q in or Q out, it depends on the turbine is a adiabatic turbine or not. There can be a heat transfer in the process. Okay, for compressor, this is turbine, this is compressor. For compressor, usually we draw this side small, this side large. Okay, you draw from the top also no problem. Okay, but the direction is opposite. Usually the small side is the lower pressure. Here also P2 larger than P1. Sorry, opposite to the turbine. Okay, and for compressor, there's the work in. Okay, there can be a heat transfer in or out as well, depending on the compressor is adiabatic or not. Okay, but for sure there is a work transfer in. For turbine, there's a work transfer out. Okay, nozzle just now, there's no work transfer at all. Okay, and pump, okay, pump do what compressor do, basically. There is a work in, and P2 will be larger than P1. Okay, the difference is pump is for liquid, compressor is for gas. It's that simple. Okay, different medium, we call it differently in thermodynamics, in mechanical engineering generally. Okay, so pump is for liquid, compressor is for gas, but they do the same thing. They increase the pressure, basically. Okay, and sometimes you may also heard about fan. Okay, the same fan that you have at home. Okay, so for fan, is almost like compressor as well. You give the work, it takes the electrical work, okay? But the purpose of fan is not to increase the pressure that much, but it's more for moving the flow. So the pressure might not be very, very high, P2 or P1, okay? But it moves the air only. Okay, so that's the difference between pump, compressor, fan, and also turbine. Okay. Now let's look at one example then. Okay, so this is compressing air with a compressor. Okay, so air at 100 kilopascal, 280 Kelvin, okay, is compressed steadily. Okay, whenever the question says steadily, it means steady state, basically, steady flow. Okay, to this pressure, this temperature. Okay, and well, this diagram, again, the way they draw is not correct already. So let me just redraw it. It should be like this. Okay. This is going in. So P1 is 100 kilopascal. P1 is 280 Kelvin. Okay. And going out is P2, 600 kilopascal. T2, 400 Kelvin. Okay. And the heat loss is 16 kilojoule per kg. Okay. In fact, this diagram, what is wrong is just it needs to be this way around. Okay. But doesn't matter. Let's complete this. So we have Q out. Okay. So sometimes the question may ask you to draw diagram like this. So do try to draw the schematic diagram whenever you solve the problem. Okay. During the process, okay, assuming the change in kinetic energy and potential energy are negligible. Okay, so determine the necessary power input to the compressor. So how much is the work input? Okay, for this to happen. So that's what the question is asking. Okay, so then the solution is, well, again, we can start by, this is air, so therefore it's ideal gas. Okay, so then our solution is really, again, Q in minus Q out. Sorry, plus work in minus work out plus E in minus E out. So all this equal to 0. Okay. No changes in the system internal energy, kinetic energy, and potential energy. So therefore 0. No change in the E over T. It's a steady system. Okay. And then here, there is no work out. There's a work in. Okay. There's a Q out. There's no Q in. Okay. And then we need to find out this. So then we just need to rearrange. Okay. So just rearrange the equation. Okay. And then Q out is basically the rate of heat transfer. Here, the question gives us in specific term. So therefore, we have to multiply with the mass. We'll get this Q dot out. Okay. Plus M dot because this is this is ideal gas. So therefore H2 we can approximate using CpT2. Okay, this we can approximate using CpT1. Okay, so then we should be able to find out work input. Okay, but if you see the solution here still looking at property table for air. Okay, so you can do that as well. Just because it's ideal gas, there's still a thermodynamic table which you can refer to. Alternatively, you can approximate using ideal gas equation because you are treating it as ideal gas. Okay, so either way, either one should give you the correct answer. Okay, so that's how we can find out the temperature, sorry, the work input, which you solve it, you should get this number here. Okay, so that's quite straightforward example here. Okay, but this is a compressor basically. And example 7 here, this is for turbine. Okay, so also quickly, I'll just go through. Okay, so the power output of an adiabatic steam turbine. Okay, so here is an adiabatic system, which means no heat transfer, and then it's a steam. So which means in this example here, we cannot treat it as ideal gas. We must refer to property table. Okay, and the inlet and exit condition of the steam are indicated in this figure. Inlet, exit. Okay, again here is drawn wrongly. Let me just, yes, it should be this way. Okay, and yes, I'm quite particular about this direction because this is how usually we draw turbine. Okay, and it's an adiabatic turbine, so therefore is fully insulated. So Q equal to 0. Okay, but there is a workout, which is 5 megawatts. So this number is given already. Okay, question one us to compare the magnitude of delta H, delta KE, and delta PE. Okay, and then determine the work done per unit mass of the steam flowing through the turbine, which means the work done per unit mass of steam through the turbine. So which means this is the E then, okay, or the delta. Okay, and then calculate the mass flow rate of the system. Okay, so then the first thing to do here, because since we have pressure, temperature, velocity, here you can see there is an altitude. Okay, so what happened is in this example, altitude is changing. So therefore, the potential energy for the flow here is not 0. Okay, so whenever there's a change in elevation in the flow, then you cannot assume this as 0. Okay, the potential energy for the system still 0 because this turbine doesn't move to a higher altitude or lower altitude, but the flow does. Okay, so because this is steam, So therefore, based on this state 1 condition, we look at the saturated table, steam table, okay? At this pressure, this temperature, you most likely find out that it's a superheated vapor. It's already beyond the saturated vapor line. So then, based on the the superheated table, you should be able to find out that H1 is this. So then you can find out H1. Okay. For H2, you notice that the questions say here, there is a X equal to 0.9. This is the quality of the mixture, 0.9, which means 0.9 is a vapor, 10% is a liquid. Okay, so which means at this pressure, okay, you have to look for the state H2 based on this equation at this pressure, of course. Just like how we learned in chapter 2 before this. Okay? Then you'll be able to find out H2. So then the change in the enthalpy is basically this. That's what the question wants us to find out, the change in enthalpy. Okay, change in kinetic energy, change in potential energy. Okay, so change in kinetic energy, of course, is just the velocity difference based on the velocity difference. Change on potential energy based on the altitude difference. Okay, so this is delta H, delta kinetic energy. I'll write in small cap. This is kinetic energy for the flow, potential energy for the flow. Okay, so again, this is not always equal to 0. It depends on the question. Okay, if there is a change in altitude given by the question, then of course you have to consider that. Okay, then the rest of it, to find out the flow energy, then really we just follow pretty much the standard step just now. Write the energy equation, then you should be able to find out the work because of the flow itself. They write as W here, but really it should write in E or theta. Okay, but it's the change in the enthalpy, change in the kinetic energy, change in the potential energy of the flow. Okay, this equation here. And then the mass flow rate is the total amount of work transfer out over this one. Okay, so this is the theta or the E, the one that written earlier. Somehow this textbook, the symbol is, they mix it up, which is quite confusing. Okay, but they're using E and theta earlier, so this should be E and theta. That's what they're referring to. Okay, so the way I see, the step for the solution is more or less the same. It's just how we find out the state, the first state, property of the first state, and then how we relate to the second state only. Okay, so that's pretty much the example for nozzle, diffuser, and then compressor and turbine. Okay, so there are a few more examples at the back here, which I wouldn't go into it because they are more or less the same, like how we see earlier. So quickly, before we move into the past year question, okay, just one more time to differentiate between all these devices. Okay, so first, nozzle and diffuser. Work in, work out, for sure, 0. Okay. For turbine, there's a work out. For compressor, there's a work in. Okay. So that's the difference between them. Okay. All of them can have heat transfer in or out. Okay. Unless it's being insulated. Okay. And then all of them has mass exchange as well. So 1. Okay. Then what about throttling valve? Okay. Throttling valve is pretty much like a nozzle. Okay. Because throttling valve, when you close it, area becomes smaller. So mass still conserved. Okay. And then also no work transfer. But whether or not there's a heat transfer, it depends on whether there's an insulation or not. Okay, so that's throttling valve, even though it's not part of your syllabus, but just to let you know. Okay, and mixing chamber, well, you have M1 here, M2 here, and this M3 must equal to the mix of the two of them because conservation of mass. Okay, there can be Q in, there can be Q out as well. Okay, but for mixing chamber, work transfer also equal to 0 because it doesn't do work or it doesn't require work to be done to the mixing chamber. It's just mixing two flow together. Okay. Heat exchanger, well, it's a bit slightly more complicated. Okay. So M1 equal to M2. Okay, because go in here, it will flow to here. So that's steady state. Okay. But at the same time, we have two different streams. So for this, it will go around the red tube here. So M3 equal to M4. Okay. And between 3 and 4, there will be heat transfer. That's the purpose of this device. To transfer from either 1 and 2 to 3 and 4. There is a heat transfer between the two of them. Okay. There can be heat transfer between here and outside as well. Okay. Unless, of course, it's being insulated. It's an adiabatic heat exchanger, then different story. Okay. And usually, not usually, pretty much all the time, heat exchanger doesn't has a work transfer as well. Okay, so really only turbine and compressor, there's a work transfer. The rest of them, there's no work transfer at all. Okay, all of them are open system, so therefore all of them have a mass exchange. Okay, so that's how we differentiate between all these devices. Okay, and the example I'll leave you to try. Okay, but lastly, okay, the last of the lecture slide really. Okay, so whenever you solve any thermodynamics problem, okay, so first of all is to define and sketch the system with energy and mass transfer across the boundary. Like all the example just now, you see the first thing I draw is the control boundary, the control volume, basically, where's the system boundary that we're analyzing. And then label, is there any work transfer, whether there's any energy transfer, whether there's any mass transfer. Okay, when you draw it out, it becomes clearer. And then whether there's a mass crossing the boundary. If yes, it's an open system. If no, it's a closed system. This is what we learned in this chapter here. This is what we learned previously in chapter 4. Okay, if it's a closed system, then mass is constant. Okay, then we just apply conservation of energy, then we can solve everything else. Okay, if it's a open system, then really the next thing we should be asking is whether this is equal to 0, the change in the mass in control volume. If yes, then it's a steady flow. Then we follow here. Conservation of mass, conservation of energy, then we find correspondingly. If it's no, then it's an unsteady flow, which there's a step to solve as well, but then it's not part of your syllabus. Okay, so rest assured that none of the question that you see will be an unsteady flow. Okay, so this is just a flow chart of how we solve a engineering problem when it comes to energy. Okay, right then. So any question up until this point? Is everything still clear? Is everything still understandable? Okay. There's a question, does that mean turbine is the only work that are not equal to 0? No, compressor as well. Compressor, there's a work input. Only turbine and compressor, the work is not 0 because there's a work transfer. Of course, one is positive, one is negative because one, the work go into, compressor consume work, so work going into. Okay, for turbine, it extract work, so work going out. Only turbine and compressor, the work is not 0. Okay, right. I hope everyone can still follow it. Okay, right then. So next, let's try to look at one past year question there. Okay, I think we only have another 30 minutes left. So let's quickly try to go through one past year question so that you can, I also make this your assignment too, so you can try that afterward. Okay, so for the example in the in the lecture note, please try to go through them, try to practice it yourself. Okay, then you probably will understand better from there. Okay, all the solutions are all given, so I guess it'll be quite straightforward for you to follow. Okay, so in your test two, okay, there will be 2 questions. This is a past year, okay, 2022, 2023. It's a 1 hour 30 minutes, not 45 minutes anymore. Okay, and 2 questions. First question will be on the closed system. Second question will be on open system. Okay. As for which one is a pure substance, which one is ideal gas, it depends on the question. Okay. But as you may see in the example earlier, if it's a pure substance, non-ideal gas, then we have to refer to thermodynamics table to find out the property. If it's an ideal gas, then we can still refer to the thermodynamic table, no problem. But we can approximate using the ideal gas equation. Okay. Right then, so Again, I wouldn't do the calculation. I would just roughly go through the step. Then I think if all you can understand what we went through in the lecture, then I think it shouldn't be a problem for you to solve this. Okay. So here it says that 1 kg of saturated water vapor is initially stored in a piston cylinder device. So piston cylinder device is basically a closed system. Okay. The temperature is 200 degrees Celsius. Then the water vapor is cooled at constant pressure. So which means pressure is constant. Okay. To a saturated liquid. So from saturated vapor to saturated liquid. Okay. So neglect the change of the potential energy and kinetic energy during the process. First, the question wants us to show the process on the TV diagram. Okay. So TV diagram. Okay, I try my best to write the curvy V. Okay. So the water is cooled from saturated vapor, which is here, to saturated liquid at constant pressure. So this is 1, this is 2. Okay, so the process looks like this. Okay, and if you remember, for TV diagram, the constant pressure line is basically this. It didn't say how much is the pressure. Okay, but that's constant pressure line. But the state changing from 1 to 2 is basically from here, 1 to 2. Okay, so that's the answer for number 1 here. It's really quite straightforward, really. Okay. Then next, determine the boundary work for the piston. Okay, so boundary work, okay, is basically pressure multiplied with volume change. Okay, but this only gives us joule per kg, so therefore we have to multiply with the mass as well. Okay, so pressure is a constant pressure, so which means we need to find out how much is this pressure. We know this temperature, which is 200 degrees Celsius. So we can refer to the saturated table. We should be able to find out this pressure. Okay. 200 degrees Celsius. If we look at the table will be provided. Okay. So 200 degrees Celsius, which is here. This is by temperature increment. So then we'll be able to know the. Wait, let me just use this instead. Okay, so we know the pressure. Okay, so it will be the saturated pressure. Okay, and volume change is basically V2 minus V1. Okay, and V2 is gas minus VF, basically. 1 kg. Okay, and then determine whether the process is compression or expansion. Then you just have to look at whether V2 is larger than V1. If it's larger, then it's expansion. If it's smaller, it's a compression. Okay. By the look at this, Vg I think should be larger than Vf. I think so. Because gas, the V for gas should be larger. Vg larger, this is smaller. So this was V2, sorry, V1, V2. So it's a compression for sure. Okay. And then last for this part A, show the process on a pressure versus volume diagram and indicate the region that represent the boundary work. Okay, so just now was a PV diagram. So if we draw a corresponding diagram, this is V, now it's P. Okay. The dome still the same, but the constant temperature line now go like this. Sorry. Okay, so this is 0.1, this is 0.2. Okay, so this is T equal to 200 degrees Celsius. Okay, and this is only half of the answer. The question also asking, indicate the region, represent the boundary work. Okay, so boundary work is basically P multiplied with volume. So we have this pressure. So this is basically the boundary work. Okay, so it's the area under the graph. P times volume, right? This multiplied with this. That's basically the boundary work. Okay, so that's how we answer the question number 4. Okay. So that's part 1. Part A, sorry. Okay. Part B, okay. A rigid tank with a volume this much, okay, initially contained a mixture of liquid water and vapor at 100 degrees Celsius with quality of 0.2, which means the overall volume is 0.1 meter cube, but 20% of it is liquid. Sorry, no. 20% is vapor. Okay. The mixture is then heated to a temperature of 150 degrees Celsius. So initially, 100 degrees Celsius. And then we heat up, which means Q in. So then it becomes 150 degrees Celsius. Okay. So assume the tank to be stationary, which means kinetic energy 0. The tank is not moving anyway, no altitude change, so this is 0 as well. Okay. So then the question wants us to determine the final quality of the mixture in the tank. Okay. So in order to solve this question here, okay, first of all, from here, we can find out the specific volume first, okay, because it's a mix of vapor and liquid, okay. So this we can calculate based on F plus X Fg. Okay, so then we know the specific volume in state number 1, in state number 2. Okay, the reason being is because it's a constant volume. It's a constant volume. It's a solid tank. So therefore, V1 equal to V2, specific volume. Okay, so once we calculate this, we know this. Okay, then it's a matter of at 150 degrees Celsius, how much is this? Okay, if this is larger than V2, then we're talking about mixture, right? Because on the TS diagram, this is Vg, okay? If our V2 is smaller, which means a mixture. If it's larger, which means it's a saturated vapor. And in this case, I think if you find the answer, you should get that V2 is smaller. So therefore it's a mixture. Okay. And then from there, you can calculate, you can find this, you can find this, and then you'll be able to find out X2. Okay. So then you know the quality of the mixture. Okay. Because in fact, the question asks you to find out the final quality. So it is, in fact, I think you solved it correctly, then it should be a mixture. Okay. And then the total mass of the tank of water. Okay. So we have this, we have this. So V is basically equal to mass multiplied with V1. So then we should able to find out the mass. Okay. And then write the energy balance of the equation. Okay. So the energy balance of the equation, Q in minus Q out plus work in minus work out, E in minus E out, that will be equal to delta U plus kinetic energy plus potential energy. Okay, we always write the full equation first. Okay. So this will be 0. No mass exchange because this is closed system. Okay. No Q out. There is Q in. No work out. Okay. There's no work out because, first of all, there's no work going out. There's no boundary work as well. If there's boundary work considered as one workout. Okay. So then you get your equation. this equal to this. Okay. And delta U basically equal to M multiplied with delta. Well, the change in internal energy between 1 and 2. Okay. And then here, determine the boundary work. Okay, because the boundary is fixed, so therefore boundary work is basically equal to 0. Okay. Sometimes the question is a mix between theoretical knowledge and calculation. Not everything needs to be calculated. Okay, because constant volume, so therefore boundary work here is basically 0. The question is just testing your understanding. Okay, and then determine the amount of heat transfer in the process. Amount of heat transfer, which is this one. Okay, so here you know M, we know M, yes, we know. Okay, M we already find out here. U2, we can find out, it's not a problem. Once we have this, U2 is basically U grid plus X2 UFG. U1 is also UF1, of course, plus X1 UFG1. This is 2, of course. Okay, so then you should be able to find out the amount of heat transfer here as well. Okay, and then show the process on TV and PV diagram with the respective saturated line. TV diagram. Okay, so what happened is the volume is constant, specific volume is the same. Okay, so this is number 2. Number 1 is really from here. Okay, because volume is constant. So it was changing from this state where the temperature is 100 degrees Celsius to 150 degrees Celsius. Okay, so obviously in this case, pressure is not constant. P1, P2. Okay, but the phase, the state is really from 1 to 2. So it is purple line. Okay. If we are talking about the PV diagram, okay, constant temperature line, 150, 100, okay, it's still changing from here, sorry, from here to here. Okay, because here V1 equal to V2. Okay, so really both are straight line going up. Okay, because it's a constant volume from, it's a rigid tank. So what we're dealing here is constant volume problem, and here is a moving boundary problem. Okay. So far, okay? With this past year question. Okay. So I think the question is more or less similar with the example as well. Okay. So give it a try. Okay. When later on after this, before Tuesday, obviously. Okay. So next, let's quickly, well, it's already 11, so I'm going to take a bit more time just to finish going through the question number 2 here. Okay. So question number 2 will be on the open system. Okay. So here the question is slightly different. Part A, B are more on theoretical, and then C is the calculation. Okay. So let's go one by one. Okay. Consider an open system with one inlet and one outlet. Okay. State that the mass content of the system, whether it's increase, decrease, or constant for the following case. So which means we have a okay. We have a mass in, we have a mass out. Okay. And the question wants us to determine the dm control volume over dt, whether it's increase, decrease, or constant. Okay. So incoming mass flow is higher than outgoing. So that obviously is increase. Incoming mass flow is lower than outgoing. That obviously is decrease. If they're the same, that obviously will be the same, constant. Okay. So it's really just testing your understanding with mass balance on here. Okay. Second, sorry, part B, is it possible for steady flow system involve boundary work? Okay. And the answer for that is not possible because for the steady flow system, okay, it basically means that volume cannot change as well. Okay, volume is constant as well. Because if volume is not changing, boundary work is basically pressure multiplied with volume. Okay, multiply with the mass, of course. Sorry, not m dot. Okay, but if volume is constant, which means there cannot be a boundary work. Boundary is not moving, it's not doing work at all. Okay, so that's the answer for part B. If the boundary is moving, then yes, there can be a boundary work. Okay. And then last part here, okay. So this here is a compressor. Compressor therefore operate A. When it's operating A, which means this question is ideal gas from. Okay. It's a compressor, which means there's a work exchange. There's work into the compressor. Okay. So it's used to compress air from 100 kilopascal, 25 degrees Celsius, to 2 megapascal, 420 degrees Celsius. Okay. The air enter the compressor at the velocity of this, okay, through the inlet area of this, okay, and exit through an area of this area. Okay. Heat loss this much occur during the compression process. So which means it's not a adiabatic compression process. There's a heat loss. Okay. So the change in potential energy is negated. There's no change in potential energy. So the airflow itself, there's no altitude change. Okay. And the air is treated as ideal gas. Very nice of the question to inform this as well, but then you should really know already because it's air. Okay, with gas constant of this and Cp value of this. So you can use this to approximate the enthalpy, for instance. Okay, and density as well. Okay, so then the question wants us to sketch the schematic diagram of the compressor and label it completely. Okay, so it's a compressor. So we draw the compressor that looks like this. Flow go in here, out from here. This is state number 1, state number 2. Okay, so inlet pressure 100 kilopascal. Okay, and velocity. Oh, sorry. It's a very bad habit to write it in a small v. It should be the straight sheriff v. 25 per second. Area 0.17. Okay, so this is the inlet state. Okay, the outlet state P2 2.0 megapascal, T2 420 degrees Celsius. A2 is 0.09 meter square. Okay, and there's a heat loss, don't forget. So Q out, because it's per kg, so therefore I write it in a small q, 18 kilojoule per kg. Okay, and this is compressor, so therefore there must be a work in. There must have. Okay, and our control boundary is basically here, the A. So there's a mass exchange, there's a heat exchange, there's a work exchange as well. Okay, so that's the answer for part 1 here. Okay, so always draw the schematic diagram, label everything, so then it's very clear. Otherwise, it's just a long paragraph, right? So draw it out. It's much easier to visualize it. Okay, and then the question wants us to determine the mass flow rate of the air. Okay, and seeing from here, inlet condition, state 1 definitely more complete. So therefore, we can calculate the mass flow rate based on here, rho A V, V in the velocity. Okay, density P over RT, because this is ideal gas. A1, we have it. V1, we have it as well. So then we should be able to calculate the mass flow rate, no problem. Okay, and then the outlet velocity. Okay, so for the outlet velocity, well, of course, this M1 equal to M2, conservation of mass. Okay, so M2 will be rho 2, A2, B2. We have pressure, we have temperature, so which means P2 over RT2. A2, we also have it. So we should be able to find out B2. This is a non-value, okay? Because we have pressure, we have temperature, so we know the density of the outlet. So this shouldn't be a problem at all. Okay. Then the power input to the compressor. Okay, so for this, of course, we have to write the energy balance. Okay, so Q1, sorry, not plus, minus QR this equal to 0 because there's no change in the internal energy, kinetic energy of the system, potential energy of the system, right? So equal to 0. And then from here, let's cross out what doesn't applicable. There's a Q out, there's no Q in. There is a work in, there's no work out. Okay, so then let's rearrange it slightly. So then for us to find Q in is basically Q out plus E out minus E in. Okay, and Q out is basically M dot Q out. Okay, M dot Q out. So this one no problem. Plus M dot H. I'll write it as theta first. Yeah? Okay. By the way, the in is 1. This is 2. But we know that they are the same. So therefore, we can just write it as 1M. Okay. And this here is really H1, sorry, this is out, so 2, H2 plus V square over 2 plus GZ2. Okay, so here H1 plus V1 square plus GZ1. Okay. So then from there, you should be able to find out work in. Okay. The question wants us to ignore the potential energy. So therefore here, even though I write the full equation, this should be 0. Okay. Catch, we can use Cp T1, Cp T2. Velocity, we have it. So shouldn't be a problem for us to find this. Okay. So just like that, we should be able to find out this. Okay. And the last one, explain without calculation what will happen if to the power input of the compressor if the outlet air temperature, which means T2, is reduced by cooling. If T2 drop, then what will happen? Okay, use the energy balance equation to support, which means this equation. Okay, what will happen if T2 decrease? What will happen to the work input? Okay, so for this, I'll let you to find out. Okay, once you're able to write this equation out, I think shouldn't be a problem for you to answer this question. Okay, right, so that's one example of a past year question, how the question may look like. Okay, and compared to your test one, I think this definitely involve much more calculation. Okay, so I think it's definitely a good idea that you try the example in the lecture note again. Okay, and practice. I think that's the only advice I can give. Once you practice a few examples, you might find that the steps are more or less the same sometimes because the question doesn't change so much, to be honest. for thermodynamics prom. Okay, right. I think that's probably enough as well for today. And I hope everyone still can follow. Okay, even though the calculation might be pretty long. Okay, so give it a try. Okay, try the example in the lecture note, and this I also make it into the assignment already. So you can find it in the e-learning. So please get it from there, and after you've completed, please upload it back to the e-learning, submit it there. Okay, don't submit to the share folder anymore. Okay, right. So that's all for today. I think that's definitely enough. There's a lot we have covered today. So thanks again for making a time tonight for the class. So good luck with your test too. Okay, so I think you still have a few more days to go through the material and try the example, everything. Okay. So any things anyone want to ask before we end the class? Okay. Right. If no, then thanks very much again, everyone. So have a good night then.
Right, sir. Thank you, sir.
Yeah. Thank you.
Thank you, Doctor.
Doctor.
Yes.
Can you upload the recording for today, just for us to refer back?
Recording. I didn't record that.
Oh, it's okay, okay.
Yeah.
Thank you,
But
Doctor.
the notes, the lecture that I draw, I can upload that into e-learning as well.
Okay, sure. Thank you, Doctor.
Okay.